All right, 6.2 notes. So today we're taking a look at exponential equations. We're specifically going to graph them. So what is an exponential equation? The standard form used to represent an exponential equation is this y equals ab raised to the x. So our x is now in an exponent. That's why we call it exponential. Our b value always has to be bigger than 0. And b cannot be equal to 1. Remember, in slope-intercept form of a line y equals mx plus b, m and b had special meanings. The same is true for a and b in this equation. So let's make a table for the following graphs that are in the form y equals b to the x. Choose 4 points, at least one positive and one negative. So if we're making a table of values right here, we have x, we have a y, right? Always the easiest number to plug in to any new equation usually is 0, right? So we take y, we say it's equal to 2 raised to the 0 power. Well, 2 raised to the 0 power is just 1, so our y value would be 1 if we plugged in 0 for x. From there, let's go positive. So if we went 1, so we'd have y is equal to 2 raised to the first power. That would be y is equal to 2. So we have a 2. Let's go negative now. So y equals 2 to the negative 1. That would give us y equals 1 over 2. So when we plug in negative 1, we get 1/2. And then it said it wants 4 points, so we'll go one more. Let's go one more positive here. So let's go 2. Y equals 2 squared, which is going to be y is equal to 4. Right? And so now we can graph these points. We're at 0, 1. We're at 1, positive 2. We're at negative 1. Positive half, so right here. And then we're at positive 2, positive 4, which would be right here. So if we're going to graph this thing, right, it's going to go up like this to the right. But let's think about what's going to happen to the left. All right, so we're going to graph it. We're going to come down through that point. And it actually, what's going to happen is it's going to stay above that line forever. All right. So some of you may know why, some might not exactly be sure, but think about that for a little bit while we graph these next couple and just kind of see what happens here. So that is the graph of A. So let's take a look at B. B, now we have a B value of 3. So let's make another XY table. Again, plugging in 0 is always a great starting point. So 3 to the 0 power is equal to 1. So that would give us a y value of 1. 1 is always great after 0. So 3 to the first power would just be 3. And then we'll go one more positive. So 2. So 3 squared would give us out 9. And then let's go 1 negative. I always like negative 1 because raising something to the negative first power is usually something pretty easy to do. So that would give us 1/3. Right? So let's take a look at what this graph is doing. At 0, we get 1 again. At 1, this time we get 3. And at positive 2, we get 9. 3, 4, 5, 6, 7, 8, 9 would be right here. And then at negative 1, we get 1/3 this time, which is going to be right down here. Again, this graph, all right, is never going to cross that x-axis. So we're just going to kind of draw against the x-axis a graph that looks just like that. My ending was not that great. Let's fix that. That's a little better. Okay. Let's take a look at C. So this time, our B value, notice, is now smaller than 1, right? So the first one we had 2, and then we had 3. Those were both whole numbers. Now we have a fraction, right? And specifically, this is a fraction that is smaller than 1. So let's see what happens when we do this. Again, XY table, start with 0 because 1/2 raised to the 0 power is just 1 because anything raised to the 0 power is 1. So then let's go 1 after that. So 1/2 raised to the first power gives us 1/2. Then let's try positive 2, right? We've been doing positive 2. Let's keep with positive 2. So 1/2 squared, right? That's technically 1 squared over 2 squared. So that gives us 1 over 4. So this would be 1/4. And then let's try negative 1, right? If we went 1/2 raised to the negative first power, that would flip this and just give us positive 2. So then we need to graph those points. So we have 0, 1 once again. This time when we go to the right, we actually go down. So it's 1/2. And then we go to the right 2. It's 1/4. So even down further. But if we go negative 1, it went positive 2, right? So then let's graph this one. It's going to look something like this. Again, still not crossing that x-axis. Okay. One more graph. We have 1/4. So let's think about 1/4 here. X, y's again. All right. Hopefully you're getting to the point where you're like, okay, we're just automatically going to plug 0 in. It gets us 1. Okay, great. If we plug 1 in, it's going to give us out the value of b, which is 1/4. We plug 2 in, it's going to square, right? So this is 1/4 squared, which is 1 squared over 4 squared, which is going to be 1/16. So really small. And then lastly, let's go negative 1. 1/4 to the negative 1 power flips it, so that's going to be 4 over 1, which is just 4. So then we have 0, 1. We have 1, 1/4, which is down here. 2, 1/16, even smaller, right? And then we have negative 1, positive 4, which would be here. So this graph looks something like this. Not my best drawing there. Okay. So those are the 4 graphs, right? Those are what exponential functions look like. 2 of the above graphs are called exponential growth, and 2 are called exponential decay. Which are which, and what do you think determines this? Create your own example of a growth and decay equation. Right? So growth. Growth means it's getting bigger. Therefore, when we look at A and B, those are both going to be growth. So A and B are growth. All right. And then our decay graphs, whoops, not A and B. Oh yeah, A and B. Sorry, what was I thinking? B is this pink color. So A and B are growth. All right, and then talking about decay, we have C and D are the decay graphs because those are getting smaller. Okay, A and B are growth, they're getting bigger. C and D are decay, they're getting smaller. So let's talk about what's determining this growth or decay. It's actually, hopefully you noticed, the B value, right? So the B value in y equals a b to the x determines growth versus decay. All right? And here's what's going to determine it. If b is larger than 1, okay, this means we have growth. So like if we have y equals 4/3 raised to the x, 4/3 greater than 1, so it's growth. Versus if 0 is less than b, but b is less than 1, meaning b is between 0 and 1, it's decay. And how do we denote decay? It would just be y is equal to, if we need an example, 2/3 x. 2/3 less than 1, so decay. One example that trips people up all too often with this growth and decay stuff is this example right here. You have y is equal to 2 raised to the negative x, right? Why does this trip people up? Because of a negative exponent. That negative exponent flips the base. So this is really y equals 1/2 x. So this is decay. Same thing would go if we're talking about a growth problem, right? You could have y equals 1/2 to the negative x. This is technically y is equal to 2 to the x. So this would be growth. All right, so you have to be careful with that negative exponent. You have to remember that it flips the base. All right, so check the above graphs with your calculator. Look at the table. Look at the table for a and b. What do you notice the graph does as the x goes to negative infinity? So if you would plug this into your y1, right, it's literally saying plug y1, set it equal to 2 raised to the x, and then plot a table of values. As the x's go to negative infinity, you're getting closer to 0. The numbers are just getting smaller and smaller and smaller and smaller. For C and D, as you go to positive infinity, the ones that are decay, so C and D, if you're going to the right on those graphs, again, you're getting closer and closer to 0. Exponential graphs have a horizontal asymptote. It says use your book to define this. Well, I'll just define it right here for those watching this video. Exponential graphs have a horizontal asymptote. So that is, it's a horizontal line that a graph approaches but never touches. Or crosses. So it never touches or crosses this horizontal line. In our example, it says what is the horizontal asymptote for the graphs above? In that case, we get the line y equals 0, right? Notice that none of these graphs cross this x-axis, which is the line y equals 0, right? So now let's investigate the same equation for the above with an a value. What transformation is this? A value is always, always, always our vertical stretch. We already have the starter points for these graphs, so let's graph them real quick. We did 0, 1 for 2 to the x, 1 to the t. When we put in 1, we get 2. When you put in 2, you get out 4. When you put -1, you get out half. This a value is saying take all of those y values and multiply them by 3. So 1/2 becomes 3/2. 1 becomes 3. 2 becomes 6. And then this 4 becomes 12, so 1, 2 above 10. So then this graph is going to look like this. All right. For B, we have 3 to the x. So that was, again, 0, 1, 1, and then up 3. 2, and then up 9. -1, we were at 1/3. So this is saying, this a value is saying take the a values and then multiply y by 1/2. So 1/2 of 1 would just be a half. 1/2 of 1/3 would be 1/6. 1/2 of 3 would be 1.5, which puts us right here. And then 1/2 of 9 would be 4.5. So that would put us right here. And there's our new graph. All right, next up we have the 1/2. So at 0, it's always 1. Hopefully you're learning that at 0, it's always that value of 1 as long as there's no other transformations going on. At 1, we got 1/2. At 2, we got 1/4. At -1, we got +2. This is telling us to take all of these values, the y values, and multiply them by 4. So now +2 becomes +8. 1 becomes 4. Half multiplied by 4 becomes 2. And 1/4 multiplied by 4 becomes 1. So there's this graph. And remember, these are still never going to cross that line, the x-axis. All right. So letter D, we have 2 multiplied by the 1/4 to the x, right? So we also have this graph 0, 1, 1, 1/4, 2, 1/16. -1 gave us +4, and now we're going to multiply all those by 2. So that's going to become +8, +2, that's going to become 1/2, and this one becomes 1/4, or no, 1/8 technically, which I guess is still right there. Not like we can really see 1/8. And then we graph that. Okay. So what conclusions can we reach about the A and B values, right? B value, we've already talked about this, but the B value determines growth versus decay. So growth or decay. The A value determines vertical stretch or shrink. All right. So those are our A and B values. If you have not yet figured out why there's a horizontal asymptote here, right, it's because this value, 1/2 raised to the x, or just b to the x in general, can never be equal to 0, right? You take 1/2, you raise it to the 1/millionth power. That's literally 1 to the 1/millionth, right, over 2 to the 1/millionth power. So that's just going to be 1 over some really massive number down here, right? Which that's really close to 0, but it's not quite 0. So therefore, we can't say that this graph is ever going to reach 0. Whatever number you plug in for x, whether it's 1 million, 1 trillion, 1 billion, it's still going to have some decimal value. So it's not quite going to be 0. That's why it has a horizontal asymptote at y equals 0. It's always going to get closer and closer to 0, but it's never actually going to touch or cross that value, right? So that's why we have a horizontal asymptote. So let's think about some of the other transformations that we have for this graph. We have y equals ab to the x minus h plus k. We've already talked about the a value. We know that h, hopefully we remember that h is horizontal shift. And k is vertical shift. So let's graph some of these with h's and k's. So it says graph the following without a calculator by getting the parent function first, which you can either consider y equals b of x, b to the x, or y equals ab to the x, and then apply the transformations. So let's take a look at y equals b to the x first. Well, I guess this one doesn't even have a value. So we need to get a parent function of y equals b to the x. So that's xy, right? We've actually already done 2 to the x, right? You plug in 0, you get 1. You plug in 1, you get 2. Sorry, I should say this is y equals 2 to the x that I'm building a table for. You plug in 2 into x, you get out 4. You plug in -1, you get 1/2. We've already built this table before. So you get 0, 1, 1 positive 2, 2 positive 4, negative 1, 1 half. Shifting these equations, all right, we technically have a horizontal asymptote right here at y equals 0. But when you shift this, the horizontal asymptote comes with it. So it's physically saying we're taking all of these points and we're moving them up 7. So 1, 2, 3, 4, 5, 6, 7. Puts us right here. Okay, so our horizontal asymptote became, instead of 0, y equals 7. So then our graph comes right through like this and looks just like this. Our domain, we can plug in any x value, doesn't matter. But the range, right, we're getting close to 7, but we're never going to reach 7. So our range is from 7 to positive infinity. Okay, let's take a look at the next one. Next graph is just negative 3, so 2 raised to the x again. 2 to the x, we already have it 0, 1, 1, 2, 2, 4, negative 1, 1 half. This negative 3 is saying take our y values, multiply them by negative 3. So that makes positive 1, negative 3. So 1, 2, 3 in the negative puts us here. Positive 2 becomes negative 6, so 4, 5, 6 puts us here. And positive 4 would become negative 12, so 7, 8, 9, 10, 11, 12 would put us right here. 1 half is becoming negative 3 halves. Whenever we have this, right, we have y multiplied by negative 3. This still exists, our horizontal asymptote. It's at y equals 0. Well, if you take that 0, you multiply it by negative 3, guess what? It's still y equals 0. So the horizontal asymptote does not move because of an a value. So then we can graph this. And it'll look just like that. Our domain, all real numbers. The range this time, though, is from negative infinity up to 0, but not including it because it never touches or crosses a horizontal asymptote. Okay, next one. We have 1 half as the b value. So again, we can make an xy table. If you plug in 0, you get 1. 1, you get 1 half. Negative 1, you get positive 2. So if that's enough points for you to see the graph, that's totally fine. Right, now we just need to make sure we shift it correctly. Our horizontal asymptote is sitting right here at y equals 0 currently. How I like to shift these is I just like to shift the horizontal asymptote. So it's saying move that down 5. So 1, 2, 3, 4, 5. So here's our new horizontal asymptote. And then all of those points are coming also down 5 to the right, or to the left 3. So this is 1, 2, 3, 4, 5, 1, 2, 3. And then this would be 1, 2, 3, 4, 5, 1, 2, 3. And then 1, 2, 3, 4, 5, 1, 2, 3. So then our graph is looking like this. So our domain, all real numbers. The range is this time going from, we have negative 5 as the lowest value, but not quite touching, up to positive infinity. Okay, last example of a graph here. So this one has a little bit of everything in it, right? We're looking at the 1 at 1/3. We have the 1/3 at the top already. We've already done, oh no, we haven't done 1/3. Just kidding, we don't have 1/3. So let's build an XY table. X's and Y's. You plug in 0, you get out 1, as always. You plug in 1, you get out 1/3. You plug in negative 1, you would get out positive 3. There's our table, right? you always need to do a value first. A value in this case is -1. So it says multiply by -1, multiply by -1, multiply by -1. So that gives us -1 here, -3 here, and then -1/3 right here. And then we're shifting all of those points up 3 and to the right 2. So we're physically taking these and we're going 1, 2, 3, then to the right 2, 1, 2. Puts us right here. Okay. We need to draw in our horizontal asymptote, right? It should just be right at +3 now because that's where it shifted, right? Y equals 0 plus 3 puts us at y equals 3. And then we can graph that, right? So it'll look something like this. And there's our graph. So domain, all real numbers. Range, coming from -infinity, going all the way up to +3. All right. So that's all the graphing stuff. It can get a little dicey sometimes. So let me know if you guys have any questions. I'd always be happy to help, maybe show you a different way to graph. But yeah. The last part here says determine if the following represents exponential growth or decay. All you have to do is you look at the b value. b greater than 1 means growth. This next example, okay, even though it's a -2, all we care about for growth or decay is the b value. B value is 5, so therefore b is greater than 1, which again stands for growth. 3/4. 3/4 less than 1, which means that this is decay. And then this last one is y equals 1/2 raised to the x. So this is a b less than 1. So this is also a decay. All right. So whenever you're talking growth or decay, you physically only need to look at the b value. Doesn't matter what is on it, what transformations are happening, just the b value. Hope this video helps. If you have any questions, as always, message me on Canvas. Have a great day.